Home security inventions you should see. Technologies designed to protect lives, property, and the future. In every generation, moments of crisis force humanity to rethink how it protects itself. Fires, floods, structural failures, and urban congestion are no longer rare events, they are increasingly common realities of modern life. As cities grow taller and populations become denser, traditional safety systems, stairs, elevators, sandbags, and permanent barriers are proving insufficient when seconds matter most. This is where modern home and building security inventions step in, reshaping the way we think about survival, preparedness, and resilience. Over the last 2 decades, advances in materials science, mechanical engineering, and emergency response design have quietly produced technologies once reserved for military, industrial, or rescue professionals. Today, these innovations are becoming accessible to private citizens, residential buildings, and commercial property owners. From controlled emergency escape systems that allow a single person to descend safely from a high-rise, to flood barriers that harness the power of water itself to resist flooding, these inventions represent a shift from passive safety to active self-rescue. This series explores not only what these inventions are, but why they were created, how they function under real-world stress, and when they become the difference between escape and catastrophe. Each part builds suspense by examining realistic emergency scenarios: fires blocking stairwells, elevators failing mid-crisis, floodwaters rising faster than warnings can spread, and then reveals how modern engineering answers those threats. Whether you are a general viewer seeking practical awareness or an expert analyzing applied safety design, this content balances accuracy with clarity. It is designed to be read, narrated, or recorded as high-quality audio, clear, engaging, and grounded in real-world performance rather than speculation. The new era of home and building security. For most of human history, the idea of home security was simple. A solid door, a strong lock, maybe a guard, a wall, or a fence if you were wealthy or powerful enough. Security meant keeping others out. Danger was imagined as something external: an intruder, a thief, an enemy at the gate. But the modern world has quietly rewritten that definition. Today, the greatest threats to life inside homes and buildings often come not from criminals, but from environmental failure, infrastructure breakdown, and time itself. Fire does not knock before entering. Floodwater does not respect property lines. Elevators stop. Stairwells fill with smoke. Power grids fail. And when these systems collapse, the most dangerous question becomes painfully simple: how do you get out or hold back the danger when everything you relied on no longer works? This is the starting point of the new era of home and building security. An era not defined by fear, but by preparedness. Not by prevention alone, but by survival engineering. When traditional safety systems are no longer enough, modern buildings are marvels of engineering. High-rises stretch hundreds of feet into the sky. Apartments stack families vertically instead of horizontally. Urban density allows millions to live, work, and travel efficiently. But this efficiency comes with a hidden cost: complex dependency. Elevators depend on power. Fire exits depend on clear air and structural integrity. Flood defenses depend on time and manpower. In emergencies, those dependencies often fail simultaneously. Consider a high-rise fire. The elevator shuts down automatically, as it should. Stairwells become the only escape route until smoke rises faster than people can descend. Or consider a coastal or riverside neighborhood during flash flooding. Sandbags require labor, foresight, and hours of preparation. But water often arrives in minutes. Traditional safety systems were designed for ideal conditions. Modern emergencies are anything but ideal. This gap between design assumptions and real-world chaos is where new security inventions emerge. The shift from passive safety to active survival. Older safety philosophy was passive. Buildings were expected to withstand danger. People were expected to wait for rescue. The new philosophy is active. It assumes rescue may be delayed. It assumes systems may fail. It assumes the individual may need to act. This shift is subtle but profound. Instead of asking, "How do we stop danger from happening?" engineers now also ask, "What tools can we give people when danger is already happening?" The answer has led to a wave of innovations that look almost futuristic but are grounded in brutally practical logic. Controlled descent escape systems. Water pressure activated flood barriers. Fire-resistant load-bearing harnesses. Modular defenses that deploy without power, anchors, or heavy machinery. These are not gadgets for comfort. They are tools for last resort moments, designed for clarity under stress and simplicity under fear. Why these inventions are appearing now? It is no accident that many of these technologies have emerged in the last 2 decades. 3 forces are converging. First, urban verticality. More people live above the ground than ever before. When you are on the 20th or 40th floor, escape is no longer intuitive. Gravity becomes both the enemy and, with the right engineering, a controlled ally. Second, climate instability. Flooding, extreme rainfall, storm surges, and unpredictable weather events are increasing in frequency and intensity. Permanent flood walls are expensive and inflexible. Temporary solutions must now be smarter, faster, and more adaptable. Third, psychological reality. People no longer assume help will arrive instantly. Disasters worldwide from fires to hurricanes have taught a hard lesson: self-rescue capability matters. Not because society has failed, but because scale and speed overwhelm even the best responders. Modern security inventions are born from this realism, not from paranoia. Engineering for the human body under stress. One of the most overlooked aspects of emergency design is the human factor. In a crisis, people do not behave like calm engineers. They panic. Their hands shake. Their breathing changes. Their ability to follow complex instructions collapses. The new generation of security systems is built around this truth. Instead of requiring training-intensive operation, many systems reduce use to 3 or fewer steps. Strap in. Clip on. Exit. Let the mechanism do the rest. Instead of relying on muscle strength, systems rely on controlled physics friction, centrifugal braking, water pressure, load distribution. Instead of assuming ideal users, they are certified across wide weight ranges, tested for uneven loads, and stabilized with multiple contact points to prevent spinning, tilting, or sudden acceleration. This is not elegance for its own sake. It is survival psychology translated into engineering. Security that works when power does not. A defining characteristic of modern emergency security inventions is power independence. Electricity is often the first casualty of disaster. Fire cuts it. Flood shorts it. Earthquakes sever it. Any safety system that depends on active power becomes unreliable precisely when it is needed most. That is why many of these inventions operate mechanically rather than electronically. Controlled descent units regulate speed through internal braking systems rather than motors. Flood barriers rely on the weight and pressure of water itself to stabilize and seal. Materials are chosen not for aesthetics but for resistance to heat, corrosion, oil, ice, and long-term environmental exposure. In other words, these systems are designed to work in the worst conditions, not the showroom. From industrial use to personal protection. Another defining feature of this era is the migration of technology. Many of the systems now marketed for residential or mixed-use buildings were originally developed for industrial, military, or rescue applications. Firefighters, offshore platforms, construction sites, and flood control operations demanded solutions long before homeowners did. What has changed is manufacturing scale and material science. Lightweight alloys, advanced polymers, and compact mechanical systems have made it possible to shrink these tools into forms that fit inside a backpack, a storage crate, or a utility room. This transition mirrors what happened with seat belts, smoke detectors, and fire extinguishers. Once specialized, now universal. The ethical dimension of preparedness. There is also a quieter, philosophical dimension to this new era of security. Preparedness is often misunderstood as fear. But at its core, it is an ethical choice. To prepare is to accept responsibility not only for oneself, but for others who may depend on you. Many modern escape and safety systems explicitly acknowledge this. Harnesses designed to carry a child or infant in front. Load certifications that allow for assisting another adult. Modular flood barriers that protect entire neighborhoods rather than single properties. These designs reflect a moral assumption: in emergencies, people do not act alone. Security, in this sense, becomes communal. Not about replacing first responders. It is important to state clearly what these inventions are not. They are not replacements for firefighters, rescue teams, or emergency services. They do not encourage reckless behavior or self-reliance at the expense of coordination. Instead, they buy time. They reduce risk. They keep people alive long enough for help to arrive or allow safe exit when help cannot. In professional emergency planning, this is known as layered safety. Each layer compensates for the potential failure of another. Modern security inventions add new layers where none previously existed. A quiet revolution, often invisible. Unlike consumer electronics or entertainment technology, these innovations rarely go viral. They are not designed to impress. They are designed to function once and flawlessly. Many people will never notice them. And if they do their job, no one will ever talk about them afterward. But history shows that the technologies that save the most lives are often the least glamorous. They operate in silence, in smoke, in darkness, in rising water. This is the context in which the new era of home and building security must be understood not as a trend, but as an adaptation to reality. Setting the stage for what comes next. In the next parts of this series, we will move from philosophy and context into specific technologies. We will examine emergency escape systems that allow controlled descent from high-rise buildings when stairs and elevators are no longer usable. We will explore how harness design, material strength, speed regulation, and stabilization work together to turn gravity into a controlled pathway rather than a deadly force. We will then shift from fire to water, analyzing flood barriers that do not fight water with weight or anchors, but instead use water pressure itself as a stabilizing ally. Each part will build on the last, not as isolated gadgets, but as elements of a broader survival ecosystem, one designed for the realities of modern life. Because in the end, security is no longer just about protecting what we own. It is about protecting the moment when everything else fails and ensuring there is still a way forward. Emergency escape systems for high-rise buildings. There is a quiet assumption built into modern life that rarely gets questioned until it is shattered: there will always be a way down. We step into elevators without thinking. We climb stairwells with the confidence that they will still be there when we need them. In high-rise living and working, vertical movement is so routine that we forget how fragile it actually is. Elevators depend on power, control systems, and intact shafts. Stairwells depend on breathable air, structural stability, and time that emergencies often refuse to give. Emergency escape systems for high-rise buildings exist because this assumption has proven false, again and again. When the vertical city becomes a trap, high-rise buildings are designed to concentrate space efficiently, not to evacuate quickly. Fire codes and safety regulations do an admirable job within realistic limits, but they are still based on probability, not certainty. They assume partial system failure, not total failure. Yet real disasters are rarely polite. A fire may start below, turning stairwells into chimneys. Smoke rises faster than people descend. Toxic gases accumulate long before flames arrive. Elevators shut down automatically, trapping occupants dozens of floors above ground with no mechanical means of escape. In such moments, height itself becomes the hazard. This is the problem emergency escape systems are designed to solve, not by redesigning buildings, but by giving individuals a personal vertical exit when shared systems are no longer usable. The concept, turning gravity into a controlled tool. At first glance, the idea of descending the outside of a building sounds terrifying. Gravity is unforgiving. A mistake of seconds or inches can be fatal. But this fear dissolves when gravity is no longer free fall, but regulated motion. Emergency descent systems do not fight gravity. They manage it. The core principle is simple: allow the body to move downward while limiting speed to a range that is safe, predictable, and mechanically enforced. This eliminates the two greatest dangers of vertical escape: uncontrolled acceleration and human error. Once clipped in, the system, not the user, controls the descent. Why these systems are backpack-sized. One of the most striking aspects of modern escape systems is their compact form. Many are designed to fit inside a backpack-like enclosure weighing roughly 30 to 35 pounds. This is not an arbitrary choice. Portability determines adoption. A system that requires installation at the moment of crisis is useless. A system that is permanently installed but occupies large space is impractical for residential use. A backpack-sized unit strikes the balance: small enough to store, large enough to contain robust mechanical components. Inside that compact volume are three essential elements. 1. A full-body harness designed for load distribution and stability. 2. A controlled descent mechanism that regulates speed automatically. 3. A fire-resistant cable long enough to reach the ground from various heights. The simplicity of this triad hides enormous engineering complexity. The harness, more than just straps. In emergency descent systems, the harness is not merely a way to attach the user to the cable. It is the interface between human anatomy and mechanical physics. A poorly designed harness concentrates force on small areas of the body, increasing injury risk and instability. Modern systems instead use wide, reinforced straps that distribute load across the thighs, hips, shoulders, and torso. This mirrors parachute harness design, where sustained suspension is expected rather than brief impact. 6 or more contact points stabilize the body, preventing rotation, inversion, or uncontrolled swinging against the building facade. Parachute-style buckles allow secure fastening even with gloved or shaking hands. Perhaps most importantly, the harness is designed to be donned quickly, under stress, without precision adjustments. This is a critical human factors decision. In emergencies, usability matters more than perfection. Certified load ranges and why they matter. One of the most misunderstood aspects of these systems is weight certification. It is not about average users, it is about worst-case scenarios. Certified carrying ranges in the United States typically span from approximately 66 pounds to nearly 300 pounds. This wide range ensures safe operation for children, smaller adults, larger adults, and situations involving carried loads. Beyond the user weight, the harness fabric itself is tested to withstand loads far exceeding normal use, often approaching or surpassing 600 pounds. This safety margin accounts for dynamic forces, uneven loading, and sudden movements during exit. Certification is not a marketing feature. It is a legal and engineering necessity. Without it, the system becomes a liability rather than a safeguard. Speed control, why 3 to 5 feet per second is critical. Free fall is lethal. Descent that is too slow, however, introduces new risks: exposure to smoke, heat, or falling debris. Modern escape systems regulate descent speed to a narrow window, typically around 3 to 5 feet per second. This range is not arbitrary. It reflects a balance between safety and urgency. At this speed, the body remains upright and stable. Impact at ground level can be absorbed safely. Heat exposure time is minimized. Panic-induced interference is eliminated. Crucially, speed regulation is automatic. The user does not brake, steer, or modulate descent. The internal mechanism does this continuously, adapting to load changes without conscious input. This removes the single greatest risk factor in emergency escape: human misjudgment. Anchoring, the most critical connection. An escape system is only as reliable as its anchor point. Modern designs assume the presence of a pre-installed structural anchor, typically rated far beyond the maximum load of the system itself. This anchor may be mounted near windows, balconies, or designated escape points. The operation sequence is intentionally minimal. 1. Strap into the harness. 2. Clip the cable to the anchor. 3. Exit the window or balcony. This three-step process reduces decision fatigue and error. The anchor itself becomes a symbol of foresight. It represents preparation made long before the emergency begins, a quiet acknowledgement that some risks cannot be eliminated, only managed. Fire resistance and environmental tolerance. High-rise emergencies rarely involve a single hazard. Fire brings heat, smoke, falling debris, and compromised surfaces. Flooding may bring water, oil, ice, or chemical exposure. Escape systems are therefore designed to tolerate extreme environments. Fire-resistant cables maintain integrity under high temperatures. Housing materials resist corrosion and thermal deformation. Internal mechanisms function despite water, oil, dust, or ice exposure. This durability is not about convenience. It is about ensuring that the system works once, under the worst conditions imaginable. Carrying children, infants, and dependents. One of the most human aspects of these systems is the acknowledgement that emergencies are not faced alone. Front-mounted attachment points allow an adult to carry a child, infant, or small animal securely during descent. This design choice transforms the system from an individual escape tool into a family survival system. The emotional weight of this capability cannot be overstated. In real emergencies, people will not abandon dependence to save themselves. Systems that fail to account for this reality fail morally, not just technically. Reuse, rewinding, and recertification. After a full descent, escape systems must be rewound and recertified before reuse. This is not a flaw, it is a feature. The forces involved in controlled descent place stress on internal components. Certification ensures that the system will perform exactly as designed the next time it is needed. In safety engineering, certainty outweighs convenience. Cost versus value. Prices for single self-rescue kits typically range from under $2,000 to just over $2,300, depending on configuration and cable length. This figure often surprises people until it is compared to what it replaces: risk, uncertainty, and dependence on conditions that may not exist during an emergency. Like smoke detectors or fire extinguishers, the true value of an escape system is measured not in frequency of use, but in the moment it works. A final thought. Emergency escape systems for high-rise buildings represent a profound shift in how we think about safety. They do not promise comfort. They do not eliminate danger. They offer something far more honest, a controlled path when no other path remains. In the next part, we will look deeper into the engineering heart of these systems, the harness itself, and explore how material science, human anatomy, and mechanical design come together to turn fear into controlled motion. Because when gravity is inevitable, control is everything. Harness engineering: how controlled descent saves lives. If emergency escape systems are the promise of survival, the harness is the promise made tangible. It is the quiet mediator between the human body and the indifferent force of gravity. In moments of crisis, when fear narrows vision and time feels compressed, the harness becomes more than equipment. It becomes trust that the body will be held, stabilized, and guided safely downward when every instinct is screaming otherwise. To understand why harness engineering is so critical, we must begin with an uncomfortable truth: the human body is not designed to be suspended. Evolution optimized us for walking, running, and climbing, not hanging dozens of stories above the ground. Every element of modern descent harness design exists to compensate for that biological mismatch. From ropes to systems, a short evolutionary backdrop. Early rope-based escapes relied heavily on user skill. Friction wraps, knots, gloves, and judgment determined whether a descent was survivable. These methods worked for trained professionals. For civilians under extreme stress, they were dangerous. The modern harness represents a philosophical break from that era. Instead of expecting humans to behave like machines, engineers designed machines to behave like reliable partners. This shift mirrors trends in aviation, automotive safety, and medicine: automate the critical functions, stabilize the human, and remove unnecessary decision-making under stress. The core problem: gravity acts on mass, not intention. Gravity does not care whether a person is calm or panicked, athletic or exhausted. It acts uniformly, accelerating mass toward the ground. In uncontrolled descent, that acceleration becomes lethal in seconds. The harness is not there to stop gravity. It is there to redistribute gravitational forces so the body experiences them as manageable load rather than catastrophic stress. This distinction between stopping and redistributing is foundational to harness engineering. Load distribution: why wide straps matter. One of the most visible features of modern escape harnesses is their width. Straps are intentionally broad, padded, and reinforced. This is not about comfort in the conventional sense. It is about physics and physiology. Narrow straps concentrate force. Concentrated force compresses nerves, restricts blood flow, and causes pain that can trigger panic or loss of consciousness. Wide straps spread the load across large muscle groups and skeletal structures: thighs, hips, pelvis, shoulders, areas naturally capable of bearing weight. By distributing force, the harness allows the body to remain functional during descent. Breathing remains possible. Circulation continues. The user stays conscious and oriented. In emergencies, consciousness is not optional, it is survival. Multiple contact points: stability over strength. Strength alone does not keep a body stable. Stability comes from balance and restraint. Modern descent harnesses use multiple contact points, often 6 or more, to anchor the body in a neutral, upright position. This prevents dangerous rotation, inversion, or uncontrolled swinging away from the building. This design choice addresses a critical risk: spin. Even slight rotation can escalate rapidly as wind, cable tension, or uneven weight distribution amplify motion. Once spinning, a person may collide with the building facade, lose orientation, or interfere with the descent mechanism. By locking the body into a stable geometry, the harness ensures that motion remains predictable, vertical, and controlled. The role of the pelvic structure. Human anatomy offers a natural load-bearing structure, the pelvis. It is strong, rigid, and designed to transfer weight between the upper and lower body. Effective harnesses anchor load primarily through the pelvic region rather than the spine or abdomen. This reduces spinal compression and protects vital organs. It also aligns the body's center of mass with the descent axis, improving balance. This anatomical alignment is not accidental. It is the result of decades of biomechanical research, borrowed in part from parachuting, climbing, and rescue operations. Parachute-style buckles, engineering for stress. In calm conditions, any buckle works. In emergencies, most buckles fail not mechanically, but ergonomically. Hands shake. Dexterity drops. Fine motor skills disappear. Parachute-style buckles are designed for gross motor use. They can be secured quickly, verified visually and tactically, and resist accidental release under load. Their failure modes are predictable, and their engagement is unmistakable. This is not convenience engineering. It is stress engineering. Certified load limits and safety margins. Harness engineering does not stop at fit and comfort. It extends into rigorous testing and certification. Certified load ranges account not only for static body weight but for dynamic forces created during movement, exit, and stabilization. A harness rated to carry users from roughly 66 to nearly 300 pounds must perform identically across that entire range. Beyond user weight, materials are tested to far higher thresholds, often approaching 600 pounds or more. This margin accounts for sudden shifts, uneven loading, and worst-case scenarios. In safety systems, margins are where lives are saved. Fabric science, strength without bulk. Modern harness fabrics are technological achievements in their own right. They must be fire-resistant, tear-resistant, flexible under load, lightweight enough for portability, durable across years of storage. High-strength synthetic fibers, advanced weaves, and layered construction achieve this balance. These materials do not melt easily, degrade under heat, or fail catastrophically when damaged. Unlike everyday textiles, harness fabrics are designed to fail slowly and visibly, providing warning rather than sudden collapse. 6-point stabilization and body geometry. 6-point stabilization refers to anchoring the body at multiple strategic locations to maintain orientation. This transforms the body from a swinging mass into a stabilized structure. The effect is subtle but profound. Instead of feeling like a hanging object, the user feels supported, guided, and aligned. Psychological studies show that perceived stability reduces panic, even in objectively dangerous situations. In emergency design, perception is as important as reality. The front attachment concept, carrying another life. Perhaps the most emotionally significant innovation in harness engineering is the front attachment system. This allows an adult to carry a child, infant, or small dependent securely in front of the torso. From an engineering perspective, this introduces complexity. The combined center of mass shifts. Load distribution changes. Stability must be maintained despite asymmetry. That modern harnesses accommodate this safely is a testament to how far the technology has evolved. It recognizes a fundamental human truth: people will not leave loved ones behind. Designing for that reality transforms a tool into a moral instrument. The psychological dimension of being held. There is a psychological element to harness design that rarely appears in technical documentation but is deeply real. Being suspended in open air triggers primal fear. The sensation of being held counters that fear. Wide straps, secure contact points, and upright posture create a feeling of enclosure, even in exposure. This sense of being held is not sentimental, it is functional. Reduced panic leads to reduced interference, smoother descent, and safer outcomes. In this way, the harness is both a mechanical and emotional stabilizer. Integration with the descent mechanism. The harness does not operate alone. It interfaces precisely with the control descent unit. Attachment points are reinforced and positioned to align force vectors, preventing torque or twisting. This integration ensures that the system behaves as a single unit rather than a collection of parts. In safety engineering, integration is where failures are prevented or created. Modern systems prioritize integration over modular improvisation. After the descent, why recertification matters. A harness that has borne full load during descent has experienced stress. Even if no damage is visible, microstrain may exist. Recertification ensures that the harness will perform to specification the next time it is needed. This requirement reflects a core principle of safety engineering: unknowns are unacceptable. A final reflection. Harness engineering may seem like a technical detail in the broader story of emergency escape systems, but in truth, it is the heart of the matter. When everything else fails, power, elevators, stairwells, time, the harness is what stands between a human body and gravity's final say. It is not dramatic. It does not promise heroism. It promises something far more valuable: controlled descent, stable motion, and the preservation of life in moments where chaos would otherwise reign. In the next part, we will explore the materials that make this possible: fire-resistant fibers, heat-tolerant cables, and the science that allows these systems to survive the environments they are designed to escape. Because in emergencies, survival is not about fighting nature. It is about understanding it deeply enough to move through it safely. Fire-resistant materials and load certification explained. Fire is one of the few forces that strips away illusion instantly. In seconds, it turns modern architecture into something ancient: heat, smoke, and instinct. In those moments, materials stop being abstract specifications on a data sheet and become the thin boundary between survivability and failure. Part 4 explores the invisible backbone of emergency escape systems: fire-resistant materials and load certification, the reason these systems continue to function when everything around them is actively trying to destroy them. Why fire changes the rules of engineering. Under normal conditions, many materials perform beautifully. Under fire conditions, most fail catastrophically. Heat weakens metals. Flames melt polymers. Smoke corrodes surfaces and infiltrates mechanisms. Toxic gases reduce oxygen and impair human judgment. Emergency escape systems are designed with the understanding that fire does not arrive politely. It arrives violently, unpredictably, and often with secondary hazards: falling debris, thermal shock, and structural movement. Fire-resistant materials are not chosen because they look durable. They are chosen because they retain integrity under stress, not just momentarily, but long enough to complete a descent. Fire resistance versus fireproofing, a critical distinction. One of the most common misconceptions is the idea of fireproof materials. In reality, nothing is truly fireproof. Engineers instead design for fire resistance: the ability of a material to maintain structural and functional performance when exposed to heat for a defined period and intensity. In escape systems, this means The cable must not fail or elongate excessively. The harness fabric must not melt, tear, or lose strength. The housing must protect internal mechanisms from thermal damage. Critical components must continue to function long enough for escape. Fire resistance is about buying time, not defeating fire. The descent cable, the spine of the system. If the harness is the interface with the human body, the cable is the spine of the entire escape system. Modern descent cables are typically constructed from high-strength steel or advanced composite materials designed to tolerate extreme heat. Steel, when properly treated, retains tensile strength at temperatures far above what standard building fires produce long enough to complete descent. But strength alone is not enough. The cable must also resist abrasion against building surfaces, kinking under load, thermal expansion that could interfere with braking systems, corrosion from smoke, water, or fire suppressants. To achieve this, cables are often coated or encased in fire-resistant sheathing that insulates the core while allowing smooth movement through the descent unit. Why melting is more dangerous than braking? When people imagine failure, they often imagine snapping. In fire conditions, melting and deformation are far more dangerous. A cable that softens can stretch unpredictably. A harness strap that melts can fail silently. A housing that warps can jam internal components. Fire-resistant materials are chosen specifically to avoid these failure modes. They may discolor, char, or stiffen, but they do not lose load-bearing function abruptly. This controlled degradation is intentional. It preserves predictability, which is essential when human lives are attached. Harness fabrics, strength under flame. Harness fabrics in emergency escape systems are not ordinary textiles. They are engineered composites. Typically, they use high-temperature synthetic fibers that resist ignition, do not drip molten material when exposed to flame, maintain tensile strength under heat, resist tearing even after thermal exposure. These fibers are often woven in patterns that prevent propagation of damage. A tear in one direction does not compromise the entire structure. This is why harness fabric strength ratings often far exceed user weight. They are designed to remain reliable after exposure to conditions that would destroy everyday materials. Heat, smoke, and chemical exposure. Fire rarely comes alone. It brings smoke, which contains corrosive chemicals, and often water or foam from suppression efforts. Escape system materials are therefore tested for resistance not only to heat, but also to water saturation, oil and chemical exposure, ice formation after suppression, long-term storage degradation. A system that survives heat but fails when wet is not a safety system, it is a liability. The housing, protecting the brain of the system. The descent mechanism, the brain of the system, lives inside a protective housing. This housing must perform multiple roles simultaneously. Shield internal components from heat. Resist deformation under thermal stress. Prevent debris intrusion. Allow controlled cable movement. Materials like corrosion-resistant aluminum alloys are often used because they balance strength, heat tolerance, and weight. Aluminum does conduct heat, but in controlled thicknesses and designs, it disperses rather than concentrates thermal energy. This prevents localized overheating that could compromise internal braking systems. Internal mechanisms function under fire. Inside the housing, precision components regulate descent speed. These components must continue to function despite elevated temperatures, variable load, contaminants like smoke and dust. Mechanical regulation is favored over electronic systems because it is inherently more tolerant of heat and environmental variability. Springs, centrifugal brakes, and friction assemblies behave predictably across wide temperature ranges. Predictability is safety. Load certification, what it really means. Load certification is often misunderstood as a simple weight limit. In reality, it is a comprehensive validation process. Certification considers static load, body weight; dynamic load, movement and acceleration; uneven load, carrying another person; shock load, initial exit forces. When a system is certified to carry users from approximately 66 to 298 pounds, that certification assumes worst-case conditions, not ideal use. Harness fabric tested to withstand nearly 600 pounds reflects an intentional safety margin, not excess. Why U.S. certification standards matter. In the United States, certification involves rigorous testing protocols governed by recognized safety standards. These standards exist to ensure that systems perform consistently across manufacturers and environments. Certification is not optional decoration. It is a guarantee that materials were tested under controlled conditions. Failure modes were identified and mitigated. Performance remains predictable under stress. For emergency systems, predictability is more important than peak performance. The ethics of over-engineering. Some critics argue that such systems are over-engineered. In consumer products, that might be wasteful. In safety engineering, it is ethical. Over-engineering creates redundancy. Redundancy saves lives. When fire compromises part of a system, another part compensates. When heat weakens one component, another carries the load. This philosophy recognizes a harsh truth: emergencies are not fair. Engineering must be testing beyond the lab. While laboratory tests establish baselines, real-world validation matters. Fire-resistant materials are often tested in simulated fire environments that replicate rapid temperature rise, smoke exposure, water application, prolonged heat soak. Only materials